Hello, everyone, and a very warm welcome. I'm Dr. Sayantika Chowdhury. Today, we're going to talk about something really cool, something that lets you build almost any digital circuit you can think of. But here's the twist. You won't need a soldering iron, just code. We're diving into programmable logic, what I like to call the ultimate box of digital Legos. So let me ask you this. Just imagine, what if you could build any digital circuit you can dream up all on a single reconfigurable chip? You know how it usually works, right? You build an adder, you wire up the gates, and that's it. It's set in stone. But what if you had a chip that could be an adder today, and then tomorrow, with just a few lines of code, you could completely change it into, say, a complex signal processor? That's the big idea here. We're moving away from fixed hardware to this amazing universal box of digital Legos that you can rebuild into anything, anytime you want.
So you're probably wondering, how on earth is this possible? Well, that's exactly what we're going to find out. Here's our blueprint for today. We'll look at how this all started, how these chips actually learn what to do, we'll meet an early hero called the PAL, and then we'll jump into the main event, FPGAs, the ultimate playground. And most importantly, we'll see why this all matters for your future. So are you ready? Let's begin. All right, so before we got these amazing reconfigurable chips, things were different, a lot more difficult. Designing a circuit was a very permanent thing. It was less like playing with Legos and more like carving something in stone. You really had just one shot to get it perfect. And making changes? Oh, that was a huge headache. So the journey from those fixed, rigid wires to the flexible silicon we use today was nothing short of a revolution. And this story, it's really a story about gaining more and more freedom. You see, back in the 70s, we got the first taste of this with PLAs. Then, in the 80s, PALs came along and made things simpler and faster. But the real aha moment, the absolute game changer, was in 1985 when Xilinx invented the FPGA. That was a huge leap. By the time we hit the 2000s, these chips were so powerful you could build entire systems on them. It completely changed the game for electronics design. Okay, so think about it. A box full of Legos is, well, it's just a pile of plastic until you get the instruction manual, right? It's the same idea here. These programmable chips are incredibly powerful, but they need a blueprint. They need someone to tell them what circuit they're supposed to become. So let's explore how we actually give them those instructions. So there are basically three ways to teach a chip what to be. First, you have fuse or anti-fuse. Think of this like writing with permanent ink. Once you program it, that's it. It's done, locked in forever. We call this one-time programmable. Then you have things like EEPROM and Flash. This is more like writing with a pencil that has a special eraser. You can write your design, and if you need to, you can erase it and rewrite it. And the best part, the information stays even when you turn the power off. That's what we call non-volatile. And finally, we have RAM-based programming. This is the most flexible of all. It's like writing on a dusty window. You can draw anything, wipe it clean, and draw something new in an instant. But there's a catch. The moment the power goes off, your drawing disappears. This is called volatility, and this little detail is super important for how modern FPGAs work. Okay, quick check to make sure you're with me. So which one of those technologies is like a whiteboard? You know, you can easily write on it, erase it, and rewrite, but it loses everything when you switch off the lights. Yep, you got it. It's the RAM-based technology. All right, let's go back in time a bit and meet one of the early superstars of this world, the PAL family. Now, if those first programmable chips were like a big generic box of Legos, you could think of PALs as the first proper Lego kit. You know, the ones designed to build something specific, like a car or a spaceship. They made building certain kinds of circuits much, much easier and faster. So what exactly is a PAL? The magic is in its structure. It's got two main parts. The first part, the AND plane, is programmable. That's your flexible bit, where you can create all your logic terms. But the second part, the OR plane, that's fixed. It's hardwired in the factory. And here's the clever bit. That limitation, that fixed OR plane, was actually its greatest strength. It made PALs simpler, cheaper, and way faster than the chips that came before them. Let's stick with our Lego analogy. Imagine your programmable AND plane is like having a huge collection of different Lego bricks. You can combine them in all sorts of ways to create your custom logic pieces. But then you have the fixed OR plane. Think of this as a special Lego base plate that has predefined spots where you can connect your creations. You can't just plug them in anywhere. So you get a lot of flexibility in what you build, but you have to fit it into this fixed, predefined structure.
This is what made it so predictable and fast. So, let's pause for a second. What's the one key feature that makes a PAL different from an earlier PLA? Think about the structure we just talked about. It's that combination, right? Programmable and plain, but a fixed or plain. That's the secret sauce of a PAL. Okay, PALs were a fantastic step forward, no doubt. But what came next? Well, it took things to a whole new level. If a PAL is like a cool Lego Technic set, then an FPGA, a field programmable gate array, that's like the biggest, most advanced Lego Mindstorm set you can possibly imagine. This is the ultimate digital playground, where pretty much everything is reconfigurable. So how does an FPGA work? The best way to think about it is like a huge, customizable city. You have thousands of little buildings, and we call these configurable logic blocks, or CLBs. Then you have a massive network of roads connecting all these buildings. These are the programmable interconnects. And finally, you have the gates and bridges that connect your city to the outside world, the I/O blocks. And the coolest part? You are the city planner. You get to decide what happens in every single building, and you draw the map that connects everything together. So you might be asking, what's the magic inside each of these little buildings? What makes them configurable? Well, it's a clever little thing called a lookup table, or a LUT. The easiest way to think of a LUT is like a tiny cheat sheet. It's a small piece of RAM, and you just program it with a truth table. So instead of physically building an AND gate, you just tell the LUT, hey, here's the truth table for an AND gate, and it will behave exactly like one. This simple, elegant idea of just storing the answers is what gives an FPGA its incredible power. So let's put these two side by side for a moment. They're really two different worlds, aren't they? The PAL has that simple, structured design, programmable and fixed or, which is perfect for smaller, super fast logic tasks. But the FPGA, that's a whole different beast. It's this massive sea of flexible logic blocks and interconnects. It trades that simple structure for almost limitless versatility. We're talking about building anything from a basic counter to an entire microprocessor, all on one chip that you can change whenever you want. Okay, that was a lot of technical detail, I know, but let's bring it all back home. Why does any of this matter to you right now as an engineering student? This is the most important part. Let's talk about your future, your career. You see, the whole journey we just took, from the rigid structure of a PAL to the massive, flexible city of an FPGA, it tells one big story. It's the story of hardware becoming more and more like software. We've gone from being stuck with limited kits to having this incredible universe of infinite digital building blocks right at our fingertips. And please, remember this if you remember nothing else from today. Understanding programmable logic isn't just about learning some old technology or memorizing block diagrams. It's about mastering a mindset of reconfigurable, flexible hardware. And that mindset, it isn't just a nice-to-have skill anymore. It's absolutely essential because this technology is powering our future. And I'm not exaggerating. Just look at where you'll find FPGAs today. They are at the heart of cutting-edge AI and machine learning. They are the backbone of our 5G communication systems. They're used in high-frequency trading where every nanosecond counts. They're in data centers, and they are even used to design and prototype the next generation of CPUs. So when you master this, you're not just learning about one chip. You're becoming an adaptable, versatile, and genuinely future-proof engineer. So, I'll leave you with this final thought. We've looked at where this all came from, how it works, and what it's made of. You now have the building blocks. You understand the power of these incredible digital Legos. So the only question that's left to ask is, what will you create?